All right. So apparently example 13 wasn't covered in your YouTube videos. So I'm going to try to go over quickly how to do that. Not quickly, just I want you to see it. I think it's a good example to go over. Okay, so number 13 on your video guide. Consider the circle r equals 1 and the cardioid r equals 1 plus the cosine of theta. Find the area of the region inside the circle and inside the cardioid. You can graph this in your graphing calculator. Get a sense for what this looks like. Oh, by the way, I'm not sure if Dr. Campbell covered this. I don't think she did. I like to set this little magnifying glass here just because it kind of shows you as your equations being graphed, you can kind of see what's happening. I like that because it just makes it a little more clear. Anyway, r equals 1 and r equals 1 plus the cosine of theta. Graph. I might be in a weird zoom here. Let me zoom standard first. Oh, you know what? My emulator. Hold on. I have this problem with my lighting. Oh. All right, do that. This. There we go. And then we'll do, oh yeah, I gotta do this. This is all because my emulator expired. I gotta do this crazy stuff. All the things you guys are missing out on by being asynchronous. I'm gonna switch my zoom just to zoom in. Oh yeah, this is so terrible. And then if you want to square it off, it looks a little bit better. You see that circle? Wow, this is like not working for me at all tonight in this lighting. But anyway, you can do this on your own calculators, no big deal. I'm gonna just recreate this graph on my paper here just so that we can see what's going on. So we have the circle, r equals 1, and then we have 1 plus the cosine of theta. So here's our circle. Kind of goes like this. Okay, so there's r equals 1. And then the 1 plus the cosine of theta goes out this way. And then you'll see it kind of does this loop up here and goes around. My cardioids are terrible. My apologies. That one wasn't too bad. All right, so this is the situation. Right now, we need to find the area that's inside both of these. Now, when we're finding the area inside both of these, that means we're finding the area inside the whole kit and caboodle. So this guy, the whole circle, and the whole cardioid. Now, if you're not sure how to do that, what I'm first going to focus on is just finding the area here. As long as I find this area outside of the circle but inside the cardioid, then I can just find the area of the circle next and add it to the area outside the circle. So first, find the area outside the circle, inside the cardioid. Okay, so we'll focus on that. So we have r equals 1 and r equals 1 plus the cosine of theta. Okay, so we're looking for the intersection point between these two graphs. Most of us are going to be able to eyeball this one. I don't want you to get into the habit of always eyeballing these because you won't always be right. Sometimes these can be a little bit deceiving. But we'll set our two equations equal to each other, and then we'll get cosine of theta equals 0. And then we're going to get theta equals pi over 2 or 3 pi over 2 down here at the bottom. We'll just focus right here on this intersection here at pi over 2. So here's my plan. I'm going to find the area of this crescent shape from theta equals 0 to theta equals pi over 2. We'll use symmetry and multiply that by 2 to get the bottom half of the area. And then we'll add that to the area of the circle. So this is for part A. So for part A, we're finding inside the circle and inside the cardioid. Okay. So our goal is to first find the area outside the circle, inside the cardioid, and then add an area of the circle. Okay, so that's my goal. You could have done this in reverse. You could have found, I don't know, you could have found this piece on the left and then added in the area of the cardioid. Kind of up to you the way you want to do that. Maybe looking ahead to part B, that'd be the easier thing to do, just knowing that you'd have to kind of go that route. It's kind of just what occurred to me first. All right, so we're using twice, and then we have 1/2 because that's what's in our formula. We're taking the integral from 0 to pi over 2. Remember, this 2 is for your symmetry. The 1/2 is part of your formula. And then you're taking, to get this area, I kind of imagine that I have, I don't know, like one of those radar blips that you see in the movies when you're on like a submarine and you're looking at the radar screen. I kind of am like watching this radial line run its way through. And when I do that, I can pick any place I would like to run this through. And no matter what, the outside area is always going to be this darker one, and the inside area is always going to be the circle. So we're going to use our formula to take the outside region squared minus the inside region squared. So the outside region is the 1 plus cos theta, so we'll square that, minus the inside region, which is 1 squared d theta. I don't want to make this video super long. You guys have done a ton of these at this point. I feel like you should be pretty comfortable with this integral, but we're taking the outside function minus the inside function. R equals 1 plus cos theta, R equals 1. You're going to expand this out, subtract 1, integrate. What you'll get here is 2 plus pi over 4. And this would be just the area of this outside piece. And then the area of the circle. Okay, we all know how to find the area of a circle. Would I really force you to use the formula for the integration here? Probably not. Pi r squared, r is equal to 1 very clearly. So pi times 1 squared is pi. If you weren't sure how to do that using geometry because you're such a calculus robot right now, the area of your circle is going to be 1/2 times the integral from 0 to 2 pi of 1 squared d theta. You'll still get pi. It's just a slightly more complicated way of getting there. So yeah, you're going to take your 2 plus pi over 4 and add pi. Let's see, so the result for your combined area, the area of the circle plus the area of the outer region is going to be pi plus 2 plus pi over 4, and you'll get 5/4 pi plus 2. That's your result. Whoops, sorry. That's your result for part A. For part B, you're looking for something a little bit different. You're finding the area of the region inside the circle and outside the cardioid. So in this case, let's see, here's our circle. All right, there's your circle. Here's your cardioid. And you're finding the region, sorry, again, you are looking for the region inside the circle, outside the cardioid. So inside the circle, outside the cardioid would be this piece. We already found this intersection point was happening at pi over 2. We found that in the previous part of this problem. So we're going to set up an integral that looks a little bit different here, but same idea. This time we don't have to do like the adding and subtracting away here at the end because we're only looking for this shaded chunk and nothing else. So this is the region for which we're trying to find the area. Now, if you can imagine you're taking that radar blip and you're sending it through, the clearest way to see it is probably right here. But remember, your formula for the area is that you're taking the outside region minus the inside, and you're taking the difference of their squares. So again, I'm going to use symmetry. So we're going to take 2 times, and then 1/2 is just part of your formula. Then we're going to take the integral from, well, in this case, our intersection happens here at pi over 2. And last time we started at 0. This time we're ending at pi. So we're going to go from pi over 2 to pi. And then we're going to take the outside, which in this case, our outside is r equals 1 squared minus our inside squared. D theta. Now, if this seems odd to you because maybe you're thinking like, well, maybe this isn't true all the time wherever I move this arrow. It actually is. It just looks different just because the shape is a little bit different. But no matter what, if I were to, move this arrow up here, you would still be looking at this little tiny sliver of area. Even though it doesn't look like there's anything there, it's infinitesimally smaller as you get to this intersection point. And then as you move your little radar blip down, eventually you get to a point where your area is going to just cover this whole piece. And you've got this infinitesimally small area down here that's being covered. So it still matters. It's still part of your function. But yeah, this will cover it all the time. So outside minus inside. Outside squared minus inside squared, I should say. And this will get you to 2 minus pi over 4. And I will let you do the work for that because you know how to do that integral, don't you? You'll use a power reducing formula. And once you expand that out, you should be good to go. All right, email me if you have questions. That is all. Good luck, you guys.